Ready when you are.
All right, so hello everyone. My name is Isabelle and I'm a high school junior from Surabaya, Indonesia. And on this occasion, I'd like to present the research project that I worked on for this year's Talaria research camp titled Learning the Four Kinematics of Continuum Robots. So to start with, you may be asking, what exactly is a continuum robot? Well, here in this slide, we have a definition taken from an existing paper by Webster and Jones, and they define a continuum robot as a continuously bending, infinite degree of freedom robot with an elastic structure. So these robots have an infinite number of joints, which allow them to have various bending capabilities. Like they're able to manipulate objects in complex environments and also navigate their way through confined spaces. Now, many continuum robots and soft robots in general are inspired by real-life biological mechanisms. Like in these two clips, you can see an example of a robot that emulates the movement of an elephant's trunk and also designed to move like the body of a snake in the other one. And one of the most prominent applications of these robots is in conducting surgical procedures like this one. And it's a very promising approach since the flexibility and accuracy of these robots, as you can see, can allow for more minimally invasive surgical procedures. And now, as I mentioned, the purpose of my research project focuses on how machine learning can be used to obtain greater accuracy and performance for a continuum robot. Now, why did I choose this topic? Well, I found it really interesting to research because continuum robotics is quite a newly emerging field of study, and it has a lot of potential for the future. So there are many advancements in the field to look forward to over time. And I also love doing this project because it combines two of my fields of interest, which are engineering and computer science. For me, it's always exciting to see what both of these fields can achieve in tandem. So moving on, I'll be summarizing my entire research project. Now, one of the most fundamental elements when it comes to modeling a robot is the kinematic framework. And there are two types of kinematic frameworks. The first one is forward kinematics, which is the one covered in this project. And its reverse version is inverse kinematics. Now, forward kinematics is used to map the position and orientation of the end effector or the end of the robotic arm from its base ring when given a set of joints on the arm. So it's like you want to figure out the distance of your fingers from your shoulder at different poses. So the joints of your arm, your shoulder, your elbow, and your wrist can be at different angles, which allow for numerous possibilities of positions. And it's basically a simple analogy of what forward kinematics does. Well, there are a few challenges when it comes to mapping the forward kinematics of continuum robots, and these can affect the robot's overall accuracy and performance. And some of these factors include friction, manufacturing errors, issues during assembly, and so on. So in this project, we tried to tackle these problems by using a data-driven approach, a machine learning-based approach. And the solution that we came up with was using artificial neural networks. And for this project, we used a specific type of neural network called multi-layer perceptron, or MLP. And it's basically applied for nonlinear functions since we're tackling nonlinear factors like the previous slide mentioned. And so in order to test and train our MLP, we used data measured from a continuum robot prototype, as you can see in the first image. So we have the curvature and length of the robot's backbone, as well as the 2D coordinates of the robot's end effector. And you can see how the curvature is increasing at a constant rate, which results in variations of coordinates. And we tested different variations of our neural network and then compared the results to find the most effective architecture. And each model we tested had a different number of layers, nodes, as well as iterations and training data. And the results we got were overall quite amusing, since we managed to achieve very low error values, with the lowest being 0.0013. And out of all the models we tested, the most effective one only had 2 hidden layers and 2 nodes each. So the structure wasn't too simple or too complex. And so, in conclusion, machine learning, especially neural networks, can serve as an effective tool to estimate the kinematics of a continuum robot with great accuracy. And besides the supervised learning approach that we used, other approaches such as reinforcement learning can also be used as an alternative solution to these kinematic problems. And although the neural network we designed for now is only suited for a planar continuum robot in 2-dimensional environments, we can hopefully extend this limitation to also work for 3D continuum robots in the future. So for this project, I worked with a mentor from the University of Toronto, and she worked at the U of T's Continuum Robotics Lab, and she was very patient and understanding and guiding me through the entire process. So I can't thank her enough for mentoring me throughout the course of this project. And it was such a fun and enlightening experience to work with someone so established in this field. And overall, I learned a lot of valuable lessons from this experience, especially with this being my first time conducting an independent research project. So I learned a lot of hard skills like scientific writing, data collecting, and so on. And I was also introduced to lots of new knowledge related to continuum robots and robotics in general. But other than that, this experience also taught me to be communicative and efficient, especially in managing my time, because I had to balance school and this project at the same time. And so as for my final remarks, well, I'd like to thank I'm really grateful to Athena and Women in STEM for providing this amazing opportunity, and especially for making it available for international students like me during this pandemic. And I'm really grateful to have been a part of this program. Hopefully I can attend Talaria again next year with another, hopefully as exciting as an experience. And that concludes my presentation. Thank you so much for listening.